Hello, my name is Ivan Evtimov, and today I'm going to be talking about our work on evaluating multimodal classification from an adversarial perspective under realistic threat models. This talk was pre-recorded on June 8, 2021, and I look forward to seeing it at the workshop on adversarial machine learning in real-world computer vision systems at CVPR 2021. It is based on work done with my collaborators at Facebook AI, who are all listed here. When we talk about multimodal models, we're going to be referring to models that classify content that has both a visual and a text component. Importantly, such models are applied in cases where it is the interaction between the modalities that determines the class of the input. What we're seeing here are examples from the hateful memes classification challenge. You will notice that for certain content, such as in this skunk image, the image alone or the text alone are not hateful. This is captured by the so-called benign confounders that are present in the dataset. I will also note that this kind of classification faces a lot of adversarial pressure since it is being applied to keep online communities safe from hateful and other harmful content. Our work here focuses on how such motivated adversaries may attempt to circumvent those models. In order to understand how adversaries may approach an attack, we first need to understand how multimodal classification works under the hood. At a high level, classification is broken into two parts. First, features are extracted from both modalities with specialized models for each of them. Then, some sort of multimodal fusion mechanism is applied in order to output the final prediction that takes into account features from both modalities. Digging even deeper, there are two primary ways of extracting features from images in particular, and each has different implications for the security of these models. On the one hand, grid feature models are your standard ImageNet state-of-the-art architecture such as ResNet with its classification layer removed. The features in that last layer that normally would serve as inputs to the classifier are used for feature extraction here in multimodal models. And then the features from grid models can be fused in one of three ways. One of them is with so-called late fusion, which just takes the average of the image and the text features. Another is by concatenation. This is also known as mid fusion. And finally, it could just be transformer based, which treats region features as dense input embeddings and combines them with text. So for example, the MMBT model that was released as part of the Hateful Memes Challenge baseline does exactly this. Now, you'll notice that these classifiers kind of are small enough that you can fine-tune them and train end-to-end on a multimodal task. This is, however, not the case with region feature models, which are based on faster RCNN or any other kind of object detection. And they use features that come from the bounding boxes that these object detectors propose. Fusion here is done with transformers. And there's at least three well-performing architectures here: MMBT, Visual BERT, and Billboard. Now, keep this distinction in mind that the faster RCNN region feature extractors are not fine-tuned end-to-end. So this means that an adversary with region feature models has access to the public off-the-shelf component that is part of the multimodal classification pipeline. Just to give you a little bit of framing on how well these models perform without adversarial intervention, well, humans, as it turns out, can do up to 85% accuracy or 83 area under the ROC curve score. And the best models that kind of get up there are based on transformer architectures with and without pre-training, specific pre-training, but they reach up to 60, 63, 65% accuracy and 70 to 71 area under the curve score. Unimodally, if you're just using one modality, unsurprisingly, you cannot do that well. And if you have some sort of simpler fusion mechanism, you get almost up there, but a few percentage points lower. So our goal in studying these models is going to be to understand how classification errors can be induced under reasonable assumptions. And importantly, we're going to try and understand if you need multimodal attacks in order to attack these models, or if attacking only one modality is enough. So what do we mean by reasonable assumptions? Well, effectively, we are going to examine a spectrum of different adversarial powers. On the one end of the spectrum, we kind of know our white box attacks, where you can just do a simple PGD algorithm or any other kind of white box attack from the literature, backpropagate end-to-end, for example, into the images, and generate adversarial examples. On the other end, we're also going to frame this with a pure black box attack, where adversaries do not know anything about machine learning, they do not know anything about the models. So these two are meant to frame both the most powerful and the least powerful adversary. But our research is going to focus in the middle here on these three varieties of gray box attacks. I will explain this gray box attacks a little bit on the next slide, but just to give you an idea of the other two, the dark gray box attack is going to assume only knowledge of an ImageNet classifier with a state-of-the-art performance, right? This is something you can get off of the internet pretty easily, so it is still a pretty weak adversary. And then on the flip side, the light gray box attacks are somewhat more powerful adversaries that have some grid features model that is trained on the task at hand, that is trained on multimodal classification. Now, I promised I would talk about this gray box attack, which assumes that you have this off-the-shelf image feature extractor. And there's a very interesting attack you can do in this case, right? So if you will notice, I mentioned that we use the faster RCNN backbone here that gives us these feature maps. And everything in the rest of the pipeline is uses these feature maps in order to make its prediction. Now, I also mentioned that the data set that we're working with, just like the skunk image, has a bunch of these benign confounders where you will find a multimodal violating image, and then you will also find an image that has the same text, but the image is replaced. Now, in order to make an adversarial image, now, for example, this violating image that we want to have classified as benign, what we're going to do is we're going to make sure that the feature maps that are extracted from the faster RCNN backbone match between the benign and the adversarial image. This can be done with something like an L2 loss and PGD. So the idea here now is that if the adversarial image outputs the feature map of a benign confounder, even while holding the text constant, the rest of the pipeline should know better than to classify this image as benign as well. Now, quick note that, of course, this is upper bounded by how well the models do well on the benign confounders, right? If the benign confounders themselves are wrong, then this strategy is going to fail, and we're going to see us hit this upper bound in a little bit. Just to give you an example of what the final images look like with different levels of adversarial power, here on the left we have the pure black box attack, which is going to be only Gaussian noise, and in the middle we have adversarial examples. You will notice that they are not particularly noticeable. These are the exact settings that we use in the results that we report next. And when we talk about results, we are going to measure the drop in accuracy on images or memes that were originally correct, right? So you can, as I mentioned, the models that we're working with do not do 100% well on the test set, so we're just going to look at this subset of memes that were originally correctly predicted, and we're going to see how many of them we can flip, and this drop in accuracy is going to be what we measure in terms of how well our attacks perform. Okay, so here are the results. Let's start with these fully black box, no access, no ML expertise models, which only achieve up to 5 or 8% accuracy. On the other end of the spectrum, full access models can, full access attacks can achieve up to 98% accuracy when attacking grid feature models. In the middle, we have pretty strong attacks as well, not 98% strong, but with access to the data set, this corresponds to the light gray box attack, where we backpropagate through a similar model and use transferability. With good feature models, we can reduce up to 44%. And with region feature models, we can reduce the accuracy by 45%. And I will note that this particular result here is bounded by the performance of the models on our target memes with matching text. And of course, if you go in the dark gray box attack, your attacks are stronger than the fully black box, no ML expertise adversary, and they can cause 11, 12 to 17% drops in accuracy. Now, one thing you will notice here is that there is no attack currently that is universal to the feature extractor. So this is maybe something the future work needs to focus on. And similarly, our focus was not on white box attacks, but there could be better methods to attack region feature models. In terms of text attack methods, there have been many different methods proposed in the literature on how to generate those, but at a high level, they kind of run in two steps. Step one, these methods select the most important word or token that contributes to the prediction. And step two, that word or token is replaced with a suitable candidate, which could be something as simple as a typo or deletion of a character, to this language modeling based word replacement that maintains the meaning but changes the prediction. Now we're going to adapt these attack methods for our own purposes. And for that end, we're going to use beam search to explore the space of different possible modifications. We're going to cap the beam search at some upper bound of edit distance. We're going to use queries to the model being attacked to know how well our selections are working during the beam search. And in terms of transformations, we're just going to stick to simple character-based augmentations, deletion, insertion, random characters, and so on. We will have three levels: light, medium, and heavy, which are just different settings of this distance metric that allows kind of the distance from the original in terms of an attack. The first thing to observe about these attacks is that they're less effective than image-based attacks that fully disrupt the text. If you look at these heavy random augmentations, the blue bar here, with full access to the classifier, only cause around 25 to 30% drops in accuracy, whereas with images we had up to 98% success in the best case with good feature models in the full access case, and in some cases with lesser adversaries we had 44 to 45%. The different success rates at different levels of access show that the adversarial power is also important here. For example, to control for the risk by an adversary who cannot query the model to an adversary who can query a similar model trained on the same data set as the target, we can look at these light random augmentations versus this dataset access guided beam search. So the yellow and the green bar are kind of adversaries with the same power, and as you can see, our guided adversary does better with 16 to 19% as opposed to 10 to 11 if they don't have access and are just randomly modifying things. As you might expect, all models perform worse when attacks across modalities are combined, and we can observe that two models in particular are the worst affected, concat-BERT and the MMBT models, and this may suggest that mid and early fusion are themselves more vulnerable to attacks than other types of fusion. So with that, thank you very much for listening, and I look forward to hearing feedback and thoughts.